Hi again. As you notice in the last couple of videos, most of the problems we have dealt with in Module 1 can be approached with Euler equation. But as I said, the real complexity of Euler equation lies on all those nonlinear terms that we have on the left-hand side, which are within the acceleration term that is very important in certain problems, and we need to take care of them. One framework that makes life easy and makes understanding of these terms and their physical meaning much better and much easier to follow is writing the equation of motion in the streamline coordinates. We call this coordinate system, if you remember, S, N, L, and this does not stand for Saturday Night Live. This is a streamline coordinate system where S is the component parallel to streamline, N is the component normal to streamline, and L is the component that is orthogonal to both of them and is coming out of the plane. In a 2D plane, we can take a look at the streamlines and think about what would be the consequence of writing Euler equation in this new coordinate system. One major difference that this coordinate system has compared to other coordinate systems such as Cartesian one is the fact that this is not anymore a rectilinear coordinate system. This is a curvilinear coordinate system, which means that unit vectors, as I move to different points in a space, are changing their orientation. Remember, Ex and Ey in Cartesian are always the same no matter where I go. But here, Es is indeed rotating based on where you are sitting on this curved streamline. That should be a cautious thing to keep in mind, and the result of that would be the appearance of certain centripetal accelerations when we write an Euler component of equation of motion normal to streamlines. But before doing that, let's see why we like to use this coordinate system. The main advantage is the simplicity we get in describing the velocity field. Velocity as a vector is not anymore something that we need to worry about all its components. Indeed, in this coordinate system, it's only the S component that becomes non-zero, and the En and the El components are both equal to 0. So that gives us a level of simplicity. At the same time, we need to keep in mind that from velocity, taking the total derivative of velocity vector, we should get the acceleration. However, acceleration, although it may be tempting to say that I only have Vs, so I should only have As, it's a little bit more complex than that. And as I said, because the coordinate system is curvilinear, although you may have a velocity vector that is only on the Es component and nothing on the En component, due to its rotation around the curved streamline, it can give you normal components of acceleration due to centripetal acceleration. So you can have both As and An, and indeed, if the flow is 2D, you will have 0 Al. So this is one of the most general ways in 2D problems you can think about velocity field and acceleration field. They are both vectors. Velocity only have one non-zero, but acceleration can have two non-zero terms. When we write down Euler equation, acceleration will go to the left-hand side. But like any other vectorial equation, we need to write down separate components of that equation and study them separately. Let's first look at the component parallel to a streamline, which we call the Es component. The Es component, the equation of motion in the Es component, becomes relatively simple. It becomes density multiplied to acceleration terms. The first term is a transient term, dvs over dt. The second term would be the advective term, which is vs dvs over ds. And this is all we have on the left-hand side. On the right-hand side, we have the gradient of the pressure with respect to S. And we have the component of gravitational field, rho g, but the S component of a gravitational constant g or vector enters our calculations. Because remember, if g, for example, is like this, we need to only take the S component of it. However, this is relatively standard and easy to understand. The En component shows us a little bit counterintuitive form. It tells us that we have a certain term that is described as rho vs squared over r, where r is the radius, local radius of curvature of the streamline. And that is the centripetal acceleration term. And on the right-hand side, we have the gradient of pressure in the n direction, dp over dn with a negative sign, plus, of course, as always, we have the body force per unit volume and the nth component of that. So you can clearly see that we have separated the problem into two sides. One is what is happening along a streamline in terms of transient acceleration or advective accelerations that can happen because the streamlines are getting, for example, converged, and you have certain acceleration that you feel as you move along them. And a separate part which is normal to streamline, and that separate part mainly tells us that you mainly get pressure gradient normal to your direction of motion if you are going around the curved streamline. And if the curve is relatively flat, which means r goes to infinity, this term is relatively negligible. But if you go around a very sharp curve, which means this r is very small, then you can actually have a considerable centripetal acceleration that should be supported by something like pressure gradient normal to that streamline. We will come back to the physical understanding of this in a moment, but let's first the ES component and see what we can do further with this.